All right. Hello, everyone. Before I begin my presentation, I would like to thank our sponsors for supporting us during these trying times. It's very reassuring to know that, unlike less fortunate people, we can continue with our semi-normal lives fairly uninterrupted. Today, I'll be presenting on my favorite topic. So for the ones that attended my workshop, the topics will overlap a little bit. But in this presentation, I'm going to show you the state of the art of what we have been doing. The overarching goal of this research is to use machine learning models to propose new workflows for upscaling physical properties of interest for the industry. Our research spans scales from the nanometers to the centimeters currently. So in this presentation, I will talk to you about the workflow that made possible obtaining a solution for the Navier-Stokes equation using convolutional neural networks. This is for fast permeability predictions. In particular, I'm gonna be focusing on the feature engineering workflow that made possible creating a general model. The main motivation for this work is that there's a huge amount of 3D data that's becoming available open source from many subsurface formations in the Earth. In those pictures, you can see some of the notable samples from our digital rock portal that are available free of charge for anyone in the world. But it's not sufficient to only download a sample and look at it slice by slice. Pore scale simulations are very important to understand how the intricacy of the structure, of the pore structure, impacts the petrophysical properties of interest. In order to carry out pore scale simulations, for the ones that are not heavily acquainted with this, we subsample our domain of interest into a small region where we want to calculate our petrophysical properties. And then we segment this sample into solid and empty voxels, as you can see to the left. In the empty voxels or porous voxels, we assign nodes throughout the domain. And these nodes are places where particles can live and travel. In particular, the case I'm showing you here is a lattice-Boltzmann simulation where we set pressure boundary conditions and we iterate the solver until our problem converges. So you can see in the image to the right our current velocity field and how it changes with each iteration. When these velocity fields stop changing, then we have reached a steady state, and we're gonna have a reliable measure of permeability if we have a well-segmented sample. The main issue with this method is that it requires a huge amount of resources. In this plot, I'm showing you some of the simulations that we ran for this project. And we can see that, for example, for a sphere pack that has a porosity of 35%, we reach convergence in no time. It basically takes a few minutes. But for a very intricate, compact sample, it can take up to 2 days running almost in 100 cores, because the more tortuous and heterogeneous the sample is, the more difficult it is for the lattice-Boltzmann method to achieve convergence. This is one of the main problems that makes it hard to deploy it as an industrial workflow. And now, Masha, I think it's time for a poll, right?
All right, yes. All right.
All right, so the first question is, since the permeability of a sample is correlated to its pore structure, a model can give an accurate estimate based on a 3D binary image only. Is this true or false? All right, over half of the population voted already. That's a good sign.
It's moving. We're going to share results in a moment. So give you another 10 seconds, true or false. You just get an image and get permeability based on and we didn't say which model. Is that open up to interpretation? All right. I'm gonna end the polling for now. Share results. There we go. Does everybody see the results?
I can put them here too.
Yes.
All right.
We have a very interesting ratio, almost 50-50.
60 to 40. All right. So want to comment?
So since the Lattice-Boltzmann method only needs a binary image to perform the simulation, our hypothesis is that a neural network model would only need a black and white, a binary image to obtain the permeability of a sample. And hopefully by the end of this presentation, I can convince the 60% that said false.
So, well, so it also somewhat depends on the method that is part of it. So that's, we did not specify the method. So this was a bit ambiguous on purpose because we are discussing what direct simulations methods can do versus what neural networks can do. All right.
So now I'm going to talk to you a little bit about the selection of our model. In general, a simpler model is always better because it's more interpretable. So it's always a good idea to start with a linear regression baseline to see how what's the correlation between inputs and outputs. And that's what petroleum engineers have been doing for a good number of decades. They try to correlate porosity with permeability. The main problem with these approaches is that these types of models, they don't perform well in the presence of heterogeneities. You can imagine this sphere back, if we fracture it, the porosity is not going to change much, but the permeability will change several orders of magnitude. So since neural networks have shown great promise at learning from vast amounts of data, we selected them for our modeling task. The next image I think is a little heavy, so sometimes it takes a little bit to load. Specifically, we employed spatially aware neural networks that are called convolutional neural networks. We chose them because they take in account the spatial structure. Convolutional neural networks train these filters that I'm showing with colorful boxes. They try to get the optimal set of parameters in these boxes to reconstruct the Lattice-Boltzmann solution in this case. And they're useful because they take in account the nearest neighbors of each point in the sample. Also, they capture multi-scale interactions because the first layers of the neural networks, they see the sample as we do, but deeper layers are able to see with a wider field of vision. And they're also good to create general models, because since we're using very tiny boxes, we can reuse them later for other samples. And if all of this sounds very obscure, I'm going to provide a more intuitive example of how these things work. They use, so we're basically trying to get the optimal set of parameters in these gray box to obtain our desired solution. So we do that by sliding it throughout our domain to obtain a feature map. And we do that multiple times until we converge to the final solution. So starting from these principles, we attempted to train a deep neural network that had a binary image as input and was trying to predict the velocity field as output by Lattice-Boltzmann as an output. So
it was using features. I'm going to be a little peanut gallery here. And that first attempt was using just like standard convolutions that are done in image processing without trying to be more aware of what's out there in porous media characterization.
Exactly. So we just threw data blindly at it. We tried to pair up our binary image, our segmented image, to the Lattice-Boltzmann solution. So we wanted to see if we could create a synthetic Lattice-Boltzmann in a neural network. So what we learned from that example was that a sufficiently deep neural network was great at learning data. So in this plot, you can see error versus training time. And the blue curve shows the error being decreased. So that means that the neural network was learning something about the data. The problem is that the orange curve shows unseen data. This is the validation curve. So we can see that at some point it starts increasing, which means that the neural network got really good with the training data, but it wasn't good at unseen examples. So our conclusion from this little exercise was that a binary image is not sufficient to create a strong relationship because it's non-unique. So then we went back to the thinking couch and thought about possible ways to improve this. So one of the main issues was that the binary image alone did not provide a unique representation of our porous material, because you can imagine that we can have very similar binary images, as in the example of the fracture and non-fracture domain, with very different velocity responses. So in order to fit a more comprehensive set of input parameters, we came up with these 4 features. These came, I will call it like expert selection. We think these 4 features represent a porous material very well. We're not claiming that these features uniquely represent a sample, but I think they can inform very well a neural network of what's happening inside a binary image. And I'll explain them a little bit. The first feature is the Euclidean distance. This tells you how far away are you from a solid wall. So in the picture to the left, you can see that the center of the pore has a really bright response, which means it's the furthest away from the solid wall. So this gives us a compact representation of pore size distribution of some sort. Then we use the maximum inscribed spheres. So this algorithm places, it tries to place the biggest sphere in a pore, and then it reduces the size of that sphere and tries to place it somewhere else until it fills completely our porous domain. And this this represents also like pore size distribution, and also the size of the throats, like the size of the constrictions. And then we use the time of flights, which they basically label the voxels based on how far away they are either from the source or the sink. So you can see in the first one, the more tortuous paths, they get a brighter color, and the more straight paths, they get more like a bluish color. This means the blue paths are kind of the preferred channels for flow. So we know that velocity is going to be really fast. The problem for when we try to check for correlations is that there's no straightforward way to see which of these features are more correlated with our velocity response, because as you can see in these plots, velocity has a positive and a negative component to it. So it has a bimodal distribution. And there's methods like mutual information that could provide a certain correlation parameter, but it's not possible to run them in very big matrices like the ones we're using, like 500 cube. So instead of doing that, instead of worrying about what feature is the most important, we gave them all to a vanilla convolutional neural network. This is kind of a state-of-the-art neural network that proved really good results in other tasks. So I gave them all of our features and asked it to produce the velocity field. So our inputs, the size of our inputs is the number of samples. That's also called a batch. Then the number of features, which in this case, it's four features that we're fitting in, and the X, Y, and Z components of these features. And we're trying to predict the velocity field. The main issue with this approach was that highly correlated features, they saturate all the neurons in the network. And let me explain that. Since intuitively Euclidean distance is the most correlated feature with velocity, the network was focusing all its efforts to pay attention to the Euclidean distance only. So it was kind of neglecting the rest of the features. And I run this experiment so you can see that more clearly. In the first plots, I'm showing what happens if we train only with the Euclidean distance. And in the second plot, I'm showing what happens when we train with all the features. And we can see that we get very similar curves. So that means that the other features are not being used. So our proposed approach to solve this problem was to craft a multi-headed network that we call the PoreFlow-Net. And these are used in Teslas, for example, because Tesla cars, they don't know which of the camera footage is going to be the most relevant to create the navigation maps. So instead, they feed them all through individual channels like this one in order to predict their 3D models. And we're doing something very similar. So instead of feeding everything through one branch, we created individual branches for each of the features. So this way we force the neural network to learn correlations from all the features that we're giving it instead of only focusing in the most important one. And this is a very interesting result because we don't have to worry too much about the correlations. The neural network is going to find the important correlations by itself. So after our image goes through the first layers of our network, this is how the input looks like. In here, I'm showing two examples. I fed the neural network once it was trained. I fed it a sphere pack and a sandstone. So you can see that in the sphere pack, the neural network prioritizes pore sizes. And that's why this is an activation map. So this is an importance map. And you can see that the neural network is saying, hey, pay close attention to kind of Euclidean distance, right? We can see that there's more weight towards the center of the pore. So the neural network is signaling that. In contrast, when we feed a sandstone, the neural network doesn't take in account that much the Euclidean distance. It says, focus on the isolated pore structures. Like this one in here, you can see this one down here, it's in yellow. So the neural network is saying like, hey, focus here because there might be some problems here. And this is all done automatically. That's the beauty of the neural networks. This is a comparison of how training our model with just the binary image and training our model with the new network and all the features looks like. We can see that the neural network is learning, but it's also generalizing. So it's also doing very well with unseen data. And in order to test all these concepts, we wanted to show how the neural network was able to generalize this problem. So what we did is we grabbed a very simple data set of sphere packs to train our neural network. And then we tested that trained neural network in several samples that were available at the Digital Rock portal. And we wanted to see like, hey, if we train it on synthetic examples, how does the neural network is going to perform on real data? Some of these, they come from micro-CT experiments. And this is a cross-section of one of those examples. This is a synthetic sandstone that's available at the portal. So to the left, you can see the Lattice-Boltzmann results. This is just a cross-section, it's a 3D sample. Then you can see the prediction of our model in the middle. And to the right, you can see the relative error. So what's notable about this is that most of the pore is resolved really well. There's some spots where the neural network has an error up to like 30%, but these are very tiny isolated spots. The relative error of this sample is like 1%. And
I mean, of the overall permeability.
Overall permeability.
Yeah.
You can see the histogram of velocities. In orange, we have the Lattice-Boltzmann velocity prediction, and on blue, we have the PoreFlow-Net or velocity prediction. And to the right, you can see the true permeability versus the predicted permeability in several of these test samples. And you can see that we're able to predict up to like 5 orders of magnitude with these networks.
And in this plot is also visible that the mismatch is the greatest for the smaller velocities, and that's probably because it's a resolution issue, essentially. So that's where the network is not, or it possibly has not seen enough features for tight spots to learn. But that's not going to affect permeability calculation all that much.
Exactly. So our publication for a while was in the most popular list of advances in water resources. It's no longer there, sadly.
Well, it dropped from 3rd to 10th recently, so we need to write another one. All right.
So the pitfalls with this approach is that it doesn't do great with very heterogeneous domains. Like if we include a fracture that spans the entire domain, or a huge bog, or maybe like shale, like if we have like a kerogen matrix, it fails. And I'm gonna explain why and what are we doing about it. It also, we're not able to change to vary the pressure. It works at a set boundary conditions for laminar flow. And also, it's confined to those like 5 orders of magnitude that I showed you previously. And we all know that porous materials are way more heterogeneous than those samples that I showed you. In nature, we have cracks like the one we're traveling through in this little animation. So what we're currently doing to address these problems is we're developing a multi-scale deep neural network that's able to take into account all the features in one sample by training several sub-networks that resolve the physics at different scales. Here are some of the results as in yesterday. We can see that in here we have a very heterogeneous sphere pack. It starts with tiny grains and then they become larger. And we can see that the network resolves this really well. And here's also a fracture, and possibly Dr. Prodanovic can tell us a little bit about this fracture more than I can.
The fracture in a natural chalk. I had a paper on it a long time back. I got an image from Australian National University. It's not quite it's part fracture, part actually a dissolution feature in a chalk sample.
You can see that using this new technique that we're proposing, we're able to resolve the velocity quite well. We also, as in yesterday, got another paper accepted on how to deal with lack of training data for more expensive simulations like molecular dynamics. It's available online if you would like to check it out.
And it's available in the folder, so I again share the link. It's a link to a folder that has both slides and it has papers. It also has people or CVs of people who are presenting.
And yeah, so my conclusion is that 3D convolutional neural networks are able to reproduce single-phase fluid patterns on natural systems with a little bit of help, right? You saw how I massaged the entire process quite well. So for the CFD experts out there, the machines are not taking over just yet. And I would like to thank our sponsors for supporting this research. And with that, I would like to open the floor for any questions that you may have.